In this video, we will discuss energy in capacitors. We will see how energy stored in a capacitor is related to the charging process of the capacitor. Next, we shall look at the concept of energy density in an electric field, namely the amount of energy contained in a given volume. Finally, we will look at a few solved problems to highlight these concepts. Next, let's look at the charging process that gives rise to the energy stored in a particular capacitor. Assume that we have a capacitor, as shown in this figure. Let's connect this capacitor through a switch, say to a battery, like that. Of course, the voltage of the battery is capital V. Initially, the plates of this capacitor has no charge, so the charge is 0 coulomb. If there is no charge, there is no electric field between the two plates of that capacitor. That means there is no energy stored in the region between the plates of the capacitor. Next, let's close this switch. Once the switch is closed, the charging process will begin. Now, this is a positive terminal of the battery, and this is a negative terminal of the battery. So the left-hand side plate of the capacitor will be charged with positive charges, and the right-hand side plate will be charged with negative charges. Let's assume at some point in time, the left-hand side plate is charged with a total charge of plus little q, and the right-hand side plate has a charge of minus little q. Let's assume the capacitor can be charged up to a maximum charge of capital Q coulomb. So as the battery tries to charge the left-hand side plate with more positive charges, let's say to the amount of delta little q, this positive delta little q will be repelled by the already existing positive charges on the left-hand side plate of the capacitor. In order to overcome that repulsion, this battery must do a certain amount of work in order to get this amount of charge and place that there. Let's call that work delta little w. Let us also assume the potential difference between the plates now is little v. So delta little w will be equivalent to that little v times the amount of charge the battery is trying to place. From the capacitor equation, we know the amount of charge on a plate is proportional to the potential difference that is being built up between the plates, and the proportionality constant is quite simply the capacitance of the capacitor. Substituting the result for V from this equation inside here, we will get the following result for the amount of work done by this battery to place this amount of charge on the positive plate of the capacitor. Next, let's rewrite that equation in terms of differential. So dW equals Q over C dQ. Let's assume that when the charging process is completed, the total charge on the plates of the capacitor is capital Q. So the work done by this battery must go on until the plates of the capacitor has this amount of charge on them. So the total work that is needed in order to accomplish this charging process is quite simply the integral of d little w, which is quite simply the integral of 1 over c q dq. Now note that this c's capacitance is a constant and can be taken out of that integral. Initially, the capacitor did not have any charge, so the lower limit is 0, and it is charged to a maximum of capital Q Coulomb. So that is the upper limit. So substituting the limits after doing the integral, we get the total work done by the battery during the charging up process of the capacitor is quite simply 1 over C Q squared over 2, or quite simply Q squared over 2C. When the charging process is complete, you cannot put any more charges on the plates of the capacitor, so the charging will simply stop. So by that time, all this work will quite be converted into potential energy within the plates of the capacitor. And this potential energy is stored in an electric field in the region between the plates. And the expression for that potential energy is simply Q squared over 2C, which is exactly the same as that. And this is the result that follows from the idea of conservation of energy, which says the amount of work done is quite simply the potential energy stored within the plates of the capacitor. Note, we can write this expression another 2 different ways, using the fact that capital Q equals capacitance times the total potential difference across the fully charged capacitor, which in this case is the same as the voltage provided by the battery. We can also write the potential energy in terms of C and V instead of capital Q and C. So substituting Q equals to CV in here, we get C squared V squared over 2C, and that's going to give you half CV squared. So we can also write the potential energy as half CV squared. Another expression is to write the potential energy U in terms of Q and V. So in this case, if you take this result, half, and you substitute C as Q over V, and then V squared, you see another alternative expression for U is half QV. So these 3 alternative expressions can be used to calculate the potential energy stored within the plates of a capacitor. Next, let's calculate the energy density in an electric field between plates of a capacitor. We are going to use parallel plate capacitor for this calculation. So this parallel plate capacitor has a plate area of A, say meter squared. The plate separation is d meter. It has an electric field, capital E, between the 2 plates. The capacitance is capital C, and the potential difference between the 2 plates is capital V. As we have mentioned a few minutes ago, potential energy stored is given by half CV squared if we choose to express the potential energy in terms of C and potential difference. We know that the expression for capacitance of a parallel plate capacitor such as this one is quite simply the permittivity of vacuum times the area of the plates over the separation distance between the plates, and V squared. Of course, we are assuming that the region between the 2 plates is quite simply filled with empty space, namely vacuum. Hence, we are using permittivity of vacuum there. Since we know the electric field times the separation between the plates is quite simply the potential difference between the plates, and using this expression in here, we get the following: half epsilon naught A over D E squared D squared. So one of the D's will cancel from the top. Rearranging this expression a little bit, you get half epsilon naught E squared A times D. Now note that A times D, namely the area of the plate times the separation distance between the plates, is quite simply the volume between the 2 plates. So this is the volume of the space where the electric field is. When you take the potential energy and you divide that by that volume, you get energy density. Let's write it as U with a subscript e, little u with a subscript e, and that is quite simply half epsilon naught square of the electric field strength. So this expression is the expression for the energy density in this electric field E. Of course, instead of vacuum, let's say the region between the plates now has some material, some dielectric material with dielectric constant K. Then, in this case, the energy density can be written as quite simply half K epsilon naught E squared. So this dielectric constant times epsilon naught is quite simply the permittivity of that dielectric material. Although these expressions are derived specifically here for parallel plate capacitor, this is a general expression that we use to compute energy density in an electric field E. Let's look at problem 1. 3 capacitors with capacitances of 8 microfarad, 8 microfarad, and 4 microfarad are connected in series, like shown here. They are connected in series across a 32 volt battery. So part A, what is the total energy of the 3 capacitors in the circuit? Of course, the best way to do this is to convert the circuit with 3 capacitors into circuit with just 1 capacitor. Like that, where the capacitance is C equivalent, and it is the same battery, 32 volts. Now we know since the arrangement is in series, the 1 over C equivalent, 1 over equivalent capacitance is 1 over 8 plus 1 over 8 plus 1 over 4. And that's going to give you 4 over 8. So that means the equivalent capacitance is quite simply 2 microfarad. The energy in this equivalent capacitor must be the same as the energy or the total energy in all these 3 capacitors. So that total energy is quite simply half equivalent capacitance times V squared, where V is that 32 volts. Substituting these numbers, you get half times 2 microfarad times 32 squared. So 2 microfarad is 2 times 10 to the power minus 6, and that will give you 1.024 times 10 to the power minus 3 joules for the energy. Another thing to note is the total charge on each of these 3 capacitors, the same as the charge on this equivalent capacitor, and that charge is quite simply 2 microfarad times 32, so 2 times 32, which is 64 microcoulomb. So each capacitor, this, and that, would have this much charge on their plates. Part B, the capacitors are now disconnected from the battery and reconnected in parallel with each other with positively charged plates connected together. Now what is the total energy of the capacitors now? Note they're connected like this, and each of them now have a charge of 64 microcoulomb, 64 microcoulomb, and 64 microcoulomb as we have calculated from part A. C equivalent for this parallel combination is just 8 plus 8 plus 4, which is 20 microfarad. The potential difference across the parallel combination is where V is the total charge divided by the equivalent capacitance. The total charge now is 64 microcoulomb times 3. So the unit is microcoulomb divided by 20 microfarad. And that's going to give you 9.6 volts, from which the total energy can be computed using the following equation. Half the total charge times the new potential difference. So the total charge is 64 times 3 times 10 to the power minus 6 to change microcoulomb to coulomb times the voltage 9.6, and that's going to give you 9.216 times 10 to the power minus 4 joules, and that completes the problem.